Hi guys, welcome to the first module of the second week on this learner space course of device physics. Today I'm going to talk about the physical interpretation of energy bands. So if you remember in the last module, we spoke about what energy bands are and why they form. Today we're going to look at what the physical interpretation of the fact that these bands exist is. Cool. So let's get started. And before we actually dive into the physical interpretation of the bands, we need to set up the context around which these bands exist, right? And the context is basically a crystal. So atoms of the semiconductor material, which is the nucleuses of these atoms, they exist in a crystal structure. And the what the energy band actually represents is the allowed energies of the electrons in the context of this crystal structure. So when we talk about an electron being free, we mean that this electron is free to move around this crystal structure. And when we try to think about what are all the different interactions that affect this, it is the and create these energy bands. It is these interactions with all these atoms in the crystal. So it's very important to remember that the context in which we are talking about this energy bands of the electrons is the crystal that the material forms. So last time we spoke about bands in the context of what are the allowed energy levels. Today, in this slide, I want to talk about how we actually fill up these energy levels. So the first fundamental rule in which, in terms of filling up this energy level, is that lower energy levels have higher stability. And there is nothing special about semiconductors here. This is like an overarching principle in physics in general, where the lower the energy of something is, the more stable it is. It's just like when you take a cup and maybe put like maybe can you imagine a hemispherical cup and you just put like a ball with some speed inside that cup, eventually it'll find the lowest point of the cup, right? Because at the end of the day that corresponds to the lowest energy. So that's the most stable point. So this is the same physics, fundamental physics principle in action. Obviously, we when we fill up the bands, we're going to fill the most stable configuration because this the likelihood of this existing is the most in nature, right? You always find things in their most stable configuration. What this means is that we start filling the bands from the lowest energy. And of course, this is absent any external source of energy. So, if you suddenly start giving energy externally to this material, we can have electrons start jumping from lower bands to higher bands. But in general, when we don't have any external source of energy, we start filling the bands from the lowest energy level. It's crucial to remember that each band can handle as many electrons as the combination of n atoms could handle at the corresponding energy level. What I mean by this is that if you have, say, the third energy level of multiple atoms n atoms coming in and combining to form a band, and say for example you could the individual atom could take 8 electrons in its third energy level. I'm just giving an example. Then even this energy band will actually have 8 into n discrete energy levels, but generally the value of n is so large that we consider it to be continuous. But in this case, it's crucial to realize that this is actually discrete, right? So it doesn't mean that you can keep filling the same energy band and never run out of space, right? So like you basically beyond a certain point you run out of space in that band, because at the end of the day even that band has a finite number of energy levels, and then you have to start moving on to the next band, right? Cool. Now the last few things on this slide is the definition of valence band and conduction band. So the uh, when we start filling up the bands in this process and fill up all the electrons that are there in the metal using this process, the highest fully filled band is called the valence band, and the band just above this is called the conduction band. So just note the word that fully filled, right? So that means it does not have any empty states in it. So if a band is partially filled and then every band above it is empty, that band would be the conduction band and not the valence band, because it would actually like the band below that would be the highest fully filled band, right? Cool. So now let's get into the physical interpretation of the conduction band specifically. So for all bands that are below the conduction band, the electrons are at least somewhat bound to their parent atom. This means that imagine that before all these atoms came into a crystal, each like all the electrons were bound around one atom. Now, when you bring all these together, they start interacting with other atoms as well, but they are still mostly bound to their parent atom. But when the electron actually reaches the conduction band, the height of the conduction band is such that the electron has enough energy to actually be free of its parent atom. What this means is that it starts to behave like a free electron in the crystal of atoms because it has got enough energy to actually go ahead and be free of the parent atom it was bound to. So what this implies basically is that all electrons in the conduction band become free to conduct electricity. What we mean by conduct is that when you will apply a voltage, or more specifically an electric field across a material, since there you have electrons that are not bound to the atoms and are free to move, these electrons move in accordance to the electric field, right? Everyone knows that if you have an electric field in the right direction, the electrons start moving towards the left in response to this field. These electrons are free to now move in the response to this field because they are not bound to any atom. So this basically that's what we mean by electrons being free to conduct electricity. Uh, Therefore, the conductivity of a material is directly dependent on the number of electrons in its conduction band. So if you increase the number of electrons that are there in the conduction band for the same electric field that you apply, you're going to have more current carriers, and those current carriers are going to conduct more electricity. That's the interpretation of this. Cool. So now I actually want to get into this concept called the band theory of solids, which basically tries to use energy bands to explain how the behavior of metals, semiconductors, and insulators is different from each other. So, in the sense that you have like these experimental observation that these type of materials behave a certain way, those type of materials behave a different way. This band theory is a theory to try and explain these observations. So this is anyway the stuff that we have already studied, but just going to study it in this context now. So, like starting with metals, right? So, metals, according to the band theory of solids, there are two cases when metals, like when you have metals. Either you have a partially filled conduction band, which is shown in this leftmost figure, or you have what is in this right figure, which is overlap between the conduction and valence band. In both cases, you have electrons that exist already in the conduction band and a significant number of electrons that are already in the conduction band. What this means is that there are current carriers readily available, which means when you apply a potential difference, these free charges readily move and constitute a current. You already have charges in the conduction band, electrons in the conduction band that are free. So this is how the band theory of solids essentially goes ahead and tries to explain how metals work. Let's talk then about semiconductors, right? So semiconductors have completely filled valence band and completely empty conduction band, and there is a small gap between these two bands. What do you mean by small gap is that the gap is of the order of the kT at room temperature, and kT is the order of the thermal energy of lattice vibrations at room temperature. What this implies is that at room temperature, some electrons get energy due to these lattice vibrations and jump from the valence band to the conduction band. And in the conduction band, they become a free conducting electron, just like you have a free electron in the conduction band of a metal. Now, the other side to this is that because you have left a more stable state in the valence band that was higher energy, periodically they also jump back to the vacancies left in the valence band to achieve this higher stability. So you do get some electrons jumping into the conduction band, but it's never as much as the metals because they tend to jump back as well. So that's why you have this like semiconductor whose name is like pretty self-explanatory. It kind of conducts and kind of doesn't, right? It's in the middle of a metal and an insulator. Uh, Finally, I want to talk about insulators, right? So insulators, just like a semiconductor, have a fully filled valence band and a fully empty conduction band. The difference between the insulator and the semiconductor is that you have a very large difference of energy between valence and conduction band. What this means is that this insulator, it's very difficult for an electron to reach the conduction band in an insulator. So what happens like because of this is that the insulator basically never conducts. Uh, Now I want to like use this band theory to like actually explain some non-trivial results, right? So firstly, in terms of what happens to the resistance of a conductor or a metal on increasing temperature, this is something we already know, right? It's something that we covered in 12th standard physics, which is that when we basically increase the temperature of a conductor or a metal, the resistance increases. The reason for this is pretty simple. If you go ahead and see the band diagram of the metal, you have a certain number of electrons in the conduction band, and this is not really going to change by a significant amount because you already have a large number of electrons. So even if you have a small change, like small increase due to the in the number of electrons due to increasing temperature, this is not going to be significant because in comparison you already have a large number of carriers. What does change significantly, however, is the amount of vibrations that you have in the lattice, and what this implies is that when these electrons are flowing through the material, every time they have a collision with the lattice, because the lattice is vibrating more violently, they lose even more energy. And if they lose even more energy, uh, the overall, on average, the conduction process becomes slower, and this is like manifested as an increase in resistance because when the lattice is vibrating more like thoroughly or violently, your overall resistance to the flow of current is more. This is why resistance of conductors or metals increases with increasing temperature. Let's now talk about a semiconductor, right? And the surprising result that you get when you actually go ahead and measure this in a semiconductor is that you see that the as you increase the temperature, the resistance actually decreases. And if you go by the theory that is used to explain the for metals, this does not seem intuitive. But we'll go ahead and see why this result is actually not all that surprising, right? So the main mechanism by which a semiconductor conducts is something we already saw, like in the slide on semiconductors, right? It's that due to the thermal energy of the vibrations, some electrons get energy to jump from valence band into conduction band, and these become the conduction electrons. These become the free electrons that can conduct. Now, when you increase the temperature, you're going to increase the likelihood of more and more electrons actually going ahead and jumping into the conduction band, because they get this extra energy to go ahead and do that. What that means when you increase that likelihood is that you have more electrons jumping into the conduction band, so you have more free electrons, so your conduction happens more easily, and so your resistance decreases. So this is why for a semiconductor the resistance decreases on increasing temperature, whereas for a conductor or a metal, this increase in number of carriers is likely to be negligible in comparison to the number of carriers you already have. But the increase in resistance due to the violent vibrations of the lattice dominates this. So I just wanted to say that already based on the physics that we have developed, I just wanted to show that a non-trivial result, like what happens to resistances of metals and semiconductors on increasing temperature, we are actually able to explain the cause behind this result. So I just wanted to demonstrate that. That's why I picked discussing this problem on this slide. Yeah, so this is the like written down explanation. You can go through it. I'll just read it for once. It's just what we discussed in the previous slide. So the temperature dependence of resistance of semiconductor, as T increases, KT increases. Therefore, the energy due to lattice vibrations increase. This subsequently means that more electrons jump from valence band to conduction band. Therefore, there are more current carriers as temperature increases, and therefore conductance increases with temperature and resistance decreases with temperature, increase in temperature. And as you can see, you can already answer some pretty non-trivial questions. So the name of this slide is a hole in our analysis so far, and the pun is intended. And what I want to point you to is that there is something in the analysis we have done that we have not yet considered. What is this thing? This thing is that in a semiconductor, we said that electrons get energy due to vibrations, and they jump uh, from the valence band to the conduction band due to this energy. But what is something subtle that we forgot to observe is that when they jump from the valence band to a conduction band, they leave an empty state in the valence band. Now, if you go back and remember how we saw the bands were filled, they were filled from the lowermost, and each state was filled, and subsequently the higher states were filled. Now, if some electron is jumping from a lower state to a higher state, it's actually leaving a vacancy in the lower state. That means there is a spot that an electron can take in the lower state that it's not taking currently. And this vacancy is something that we call a hole. And it like the fact that we haven't yet considered it actually has some pretty interesting consequences when you do go ahead and actually consider what happens due to this. So, in terms of what happens when you start considering holes, I'm going to make two claims, and basis of those two claims, I'm going to make a conclusion. The first claim is that the existence of this hole contributes to current in addition to the current contributed by a free electron. What I mean by this claim is that we saw how a free electron conducts current by moving opposite to the direction of the electric field in the conduction band, because once it reaches the conduction band, it becomes a free electron. So we saw that free electrons can contribute to current. The claim is saying that the existence of this hole contributes to current in addition to this current. So I'll get into the justification of these claims in a bit, but I just want to clear out what that claim means. The second claim is that the current contributed by the hole is as if the hole behaves like a positively charged particle. So everywhere where you had a hole, if the hole were to have been replaced by a positively charged particle of charge equal to the charge of an electron, and we were to view its movement as a positively charged particle and calculate the current would be exactly equivalent to that. That is what the second claim is. And based on these two claims, we derive the conclusion that the hole behaves like a positively charged free carrier in the valence band. So, just like electrons behave like a negatively charged free carrier in the conduction band, holes behave like positively charged free carrier in the valence band. So, now just I want to get into the justification of these claims, since the conclusion follows directly from the claims themselves. So, firstly, I want to justify to you that the existence of this hole contributes to current. Look at this diagram on the right. So we have hole. We are just looking at one row, right? And this, as you go the images downward, just imagine it as a movement in time, right? So this is our row of electrons. We had all these electrons filled in this state of equal energy, and now we are looking in terms of like which states we are occupying as a function of x, right? So just imagine this to be the spatial dimension, the x-axis. Now, when you actually go, when something jumps from here to a higher conduction band, you have this hole over here, which is depicted like this. Now, when you have this hole that gets created in the valence band, and you apply an electric field, say you apply the electric field from left to right, okay? You apply the electric field from left to right. What happens to all these other electrons, right? In the absence of this hole, before this electron jumped, these electrons, other electrons could not have done anything or tried to move towards the left because there was no vacancy for them to move, right? But in light of the new circumstances, it's possible for these electrons to actually start moving opposite to the direction of the electric field. What that basically does is that one by one, as these electrons start moving and taking the new vacancy created by the hole, it appears as if the hole is moving to the right. So this first electron takes this vacancy of the hole because it's acted upon by the electric field, and that causes the hole to move towards the right. Subsequently, more electrons jump into the place of the hole, and where the place where they jump from, that place itself becomes a hole because that place now becomes vacant. So what that means is that your electrons are in an orderly fashion moving towards the left, and your hole is in an orderly fashion moving towards the right. Now, if you look at the first figure and the last figure, it looks just like the electron has moved one space, or like this electron has moved from this rightmost end to this leftmost end. So all it appears as if these four electrons are in this figure as well and in this figure as well. But this electron has moved from the rightmost end to the leftmost end as you have progressed in time, right? What that means is that if you have a net flow of charge from one point to another, that has constituted a current. So I think I've proved to you the first claim that the existence of this hole has contributed to an extra current in addition to the current contributed by the free electron. Now, the second claim is, I think, something you can probably already see. It is as if the hole behaves like a positively charged particle, which is that if the only difference between this topmost figure and bottommost figure is that the rightmost electron has now moved towards the leftmost space. And remember, this is not like I'm not physically saying that the rightmost electron has moved to the leftmost place and everything else has remained the same. But if you compare the initial and final figure, that is the only difference. if you do, like if you compare it mathematically, you don't care which name you give to what electron. The only difference is that this electron has moved from here to here. Now, electron being a negative charge, the amount of current that will be caused in the same time for this to move from here to here is the same that amount of current if there were a positive charge here would move from here to here, right? So what that essentially means is that you have like this electron moving from right to left is same as hole moving from left to right. So the current contributed by the hole is as if the hole behaves like a positively charged particle, and therefore we can derive the conclusion that the hole behaves like a positively charged free carrier in the valence band. Uh, I just realized that I was pointing to stuff with a cursor, and that cursor is not going to be visible in the final video. So I'll just point with like some type of pointer that you're going to be able to see. So what I was essentially saying is that initially you have a hole right here, right? This is a hole. Now this hole gets first replaced by this electron because this electron sees a vacancy, sees electric field, and it replaces, and then that creates a hole in the place of that electron, right? And similarly, you have subsequently more electrons start jumping like this and kind of creating holes and moving. If you have the direction of the electric field like this, so you have electric field in this direction, then your electrons move from right to left in the opposite direction of the electric field, and it appears as if your hole is moving from like left to right as time progresses, right? So yeah, that is what I was trying to say. And uh, with respect to if you see the first and the last, and if you see like what's the difference in the charge distribution, purely mathematically, the only difference between the initial state and the final state is that you in the initial state the rightmost position was occupied and the leftmost position was empty, and now the leftmost position is occupied and the rightmost position was is empty. So uh, what I was essentially trying to tell you is that in terms of electron movement, it's as if this rightmost electron has moved from its rightmost position to its leftmost position, and every other electron stayed the same. And that is the corresponding current you have. But that can equivalently be seen as the whole being a positive charge and moving from the leftmost position to the rightmost position. So negative charge moving to the left and positive charge moving towards the right. In terms of current, it implies the same thing. And that was the justification for this statement that the whole behaves like a positively charged free carrier in the valence band. Semiconductors are like an athlete. Doping improves performance. So in this section, I just generally want to talk about doping. So, firstly, starting with what is doping? Doping is mixing our silicon semiconductor with donor or acceptor impurities. Now, if these terms are confusing, don't worry, I'll explain exactly what they mean. But let's talk about some of like the electron distribution, right? So we know that from chemistry that silicon has four outer shell electrons. Now doping basically means that you mix silicon with some other material. Now if you mix silicon with a material or impurity like boron, boron has three electrons and it is called an acceptor impurity. Why it is called an acceptor impurity is something we'll see now. So now imagine you have a crystal full of silicons, right? Like see go back to the slide on crystals and see how the crystal looks if you want to visualize. But imagine you have a crystal full of silicon and you replace one of the silicons with a boron. What this means is that for the same number of energy levels that you had, now you have one less electron because the boron has only three electrons to fill, right? So now, if you had all your energy bands and everything as the same, now suddenly you have one less electron to fill. This means that in the valence band, you have created one extra hole because you have a vacant state that you have not filled. This is why boron is called an acceptor impurity, because it creates a hole, and a hole is an electron acceptor. Similarly, now if you have an impurity like nitrogen, nitrogen has 5 electrons. So when the nitrogen replaces the silicon in the crystal structure, for the same number of energy levels in the band diagram, you have one extra electron. Now this extra electron does not have anywhere to go in the valence band, right? If because the valence band is already completely filled, and this means that the extra electron gets created in the conduction band. Just note this typo. This is not valence band, it's conduction band, because the valence band is already full. I must have copy pasted from up, that's why the typo has come. But essentially nitrogen brings with it, for the same band diagram, an extra electron. For the same band diagram, it brings with it an extra electron, which means that this extra electron has to be like accommodated in the conduction band. So TLDR of this slide is that boron creates an extra hole in the valence band because it comes with like one less electron for the same band energy, and nitrogen type impurity creates an extra electron in the conduction band because it comes with an extra electron for the same band energy diagram. So yeah, that's what happens when you mix these impurities. Now, essentially, you what mixing these impurities, what it does is that you start getting extra free charge carriers, right? Because every single boron you create, you get an you mix, you get an extra hole for that, or every single nitrogen you mix, you get an extra electron for that. So I've given an example. So even if you have mixed impurities in the order of 1 in 10 raised to 10, which means in 10 raised to 10 atoms of silicon, you mix one atom of boron. Then for a sample of like around the size of what we are comfortable with, which is around 1 mole, you have 10 raised to 23 silicon atoms. For this sample size, you actually create 10 raised to 13 extra current carriers. For the acceptor impurity type, you create 10 raised to 13 extra holes. For the donor impurity type, you create 10 raised to 13 extra electrons. And what happens due to this is that the conductivity of the semiconductor drastically changes. It drastically increases simply because you now have so many more free electrons or free holes that are available to conduct, right? So just by mixing some impurities, you can vastly change the conductivity of the semiconductor. Now, like some people might ask that why do dopants give rise to these carriers? So let's just take an example of a donor type of dopant. So you might ask that won't the final electron be like bound to the atom of nitrogen, right? So the reason this doesn't happen is that it is much easier to ionize this dopant in the semiconductor material because you have this interactions with the surrounding atoms in the crystal, as compared to in vacuum you don't have these electrons. So that's why this dopants very easily give rise to these carriers, because it becomes very easy to ionize them. Yeah, so final uh, TLDR of this slide is that doping can give a drastic change to the conductivity simply by creating some extra charge carriers. Even doping like a very small amount can like very significantly change the number of free current carriers that you have. Cool. Now let's just go into the types of semiconductors you can create by doping. Just so that you know the name. When you don't dope a semiconductor, that's something that's called an intrinsic semiconductor, because you're using the its intrinsic property without mixing anything from the outside. Now, we have two types of semiconductors, P type and N type. P stands for positive, N stands for negative. So, a material which has acceptor impurities, which we see, like for example, you have boron, uh, it creates positive type current carriers, which are holes, and is called a P type semiconductor. So you can clearly see in the right half figure, you have the impurity boron, and this creates an extra hole because it brings with it only 3 electrons. Whereas on the left side, you have a donor impurity, and this brings with it an extra electron, so it contributes to free electrons. So, donor type impurity corresponds to free electrons. It creates negative type current carriers, which are electrons, and that's why it's called N type semiconductor. So, this is just the terminology of P type and N type. Cool. Finally, the key takeaways in this module, firstly, is that everything we are talking about happens in the context of crystals. Secondly, bands are filled from bottom to top in terms of energy. Thirdly, any electrons in the conduction band are like free current carriers and are not bound to any atom. And the conductivity of the material directly depends on the number of such electrons. Fourthly, we talked about the band theory of solids and how it explains the behavior of metals, insulators, and semiconductors. Fifthly, we spoke about the how the hole behaves like a positively charged free current carrier in the valence band. And finally, we spoke about doping. Doping with donor or acceptor impurities generates excess free current carriers of negative or positive type depending on the type of impurity that you add. Yeah, so this is all for this module. You guys can ping me if you have any doubts. I'll be happy to answer them. And I hope to see you next time.